The Roman aqueduct. A structure designed to transport water from distant sources to urban centers. Tonight, we will examine the engineering principles, construction methods, and technical specifications of these water distribution systems. The word aqueduct derives from the Latin aqua, meaning water, and ducere, meaning to lead. Roman engineers constructed aqueducts throughout the empire from approximately 312 BCE to the 4th century CE, a period spanning roughly 700 years. The first Roman aqueduct was the Aqua Appia. Construction began in 312 BCE. The project was commissioned by Appius Claudius Secus, who served as censor. The censor was a Roman magistrate responsible for public morals and public works. The Aqua Appia was 16.4 kilometers long. It ran almost entirely underground. The source of the Aqua Appia was located along the Via Prenestina, a road extending east from Rome. The intake structure was positioned at an elevation of approximately 30 meters above sea level. The outlet was located near the Forum Boarium in Rome, at an elevation of approximately 20 meters. This created a gradient of 10 meters over 16.4 kilometers. The gradient of an aqueduct determined the flow rate of water. Roman engineers calculated gradients with considerable precision. A typical gradient ranged from 0.1% to 0.5%. This means the channel descended between 1 and 5 meters for every 1,000 meters of length. The gradient of the Aqua Appia was approximately 0.06%, exceptionally shallow. This shallow gradient required careful surveying. Roman surveyors used an instrument called a chorobates. The chorobates was a wooden beam approximately 6 meters long. A groove ran along the top of the beam. This groove could be filled with water to indicate level. Vertical supports at each end of the chorobates held plumb lines. When the water in the groove was level and the plumb lines hung true, the instrument was properly positioned. Measurements could then be taken. By moving the chorobates forward in stages, surveyors could establish the elevation profile of a proposed route. The construction of the channel varied depending on whether the aqueduct ran underground or above ground. Underground sections were built as tunnels. These tunnels were typically rectangular in cross-section, measuring approximately 0.6 meters wide and 1.8 meters high. The tunnel walls were constructed from stone blocks or cast concrete. Roman concrete, known as opus cementitium, consisted of lime mortar mixed with volcanic ash and aggregate. The volcanic ash, called pozzolana, came from deposits near Mount Vesuvius and other volcanic regions. Pozzolana reacted chemically with lime to create a hydraulic cement, a cement that could harden underwater. This property made it particularly suitable for aqueduct construction. The aggregate consisted of broken stones, brick fragments, or pottery sherds. Typical aggregate size ranged from 2 to 10 centimeters in diameter. The mixing ratio varied, but a common proportion was 1 part lime to 2 parts pozzolana to 4 parts aggregate. The mixture was prepared in shallow pits near the construction site. Workers mixed the components with shovels and hoes. Water was added gradually until the mixture reached the desired consistency. The concrete was placed in wooden forms. These forms, called formwork, shaped the concrete as it cured. After several days, the formwork was removed. The concrete continued to gain strength over weeks and months. Some Roman concrete structures have survived over 2,000 years. The interior surface of the channel was lined with a waterproof coating. This coating, called opus signinum, consisted of crushed pottery mixed with lime mortar. The pottery fragments were typically from broken roof tiles or amphorae. The fragments were crushed to a fine powder, then mixed with lime in a ratio of approximately 3 parts crushed pottery to 1 part lime. The opus signinum was applied in layers. The first layer, approximately 1 centimeter thick, was spread across the channel floor and walls. A second layer was applied after the first had partially cured. The total thickness ranged from 2 to 5 centimeters. The surface was smoothed with wooden floats. Above-ground sections of aqueducts were supported by arcades. These arcades consisted of a series of arches built from stone or brick. The arches transferred the weight of the water channel to vertical piers. The piers were spaced at regular intervals, typically 5 to 10 meters apart. The design of Roman arches followed consistent principles. Each arch consisted of wedge-shaped blocks called voussoirs. The central voussoir at the top of the arch was the keystone. The keystone locked the other voussoirs in place, creating a stable structure. The voussoirs were carefully cut from stone blocks. Tufa, travertine, and limestone were common materials. Each voussoir was shaped so that its sides tapered toward the center of the arch. This taper ensured that the weight of the arch compressed the voussoirs together rather than forcing them apart. The piers supporting the arches were constructed from mortared rubble or concrete faced with stone or brick. The width of the piers varied depending on the height of the arcade. Taller arcades required wider piers to ensure stability. A typical pier might measure 2 to 3 meters wide at the base and 1.5 to 2 meters wide at the top. The water channel rested on top of the arcade. This channel, called the Specus, was typically rectangular. Dimensions varied, but a common size was 1 meter wide and 1.5 meters high. The Specus was covered with stone slabs or vaulted brick to prevent contamination and evaporation. Access shafts were built at intervals along the aqueduct. These shafts, called putei, allowed workers to enter the channel for inspection and maintenance. Putei were typically spaced every 70 to 80 meters in underground sections. They extended from the surface down to the channel floor, providing access and ventilation. The Aqua Marcia was the third aqueduct built to supply Rome. Construction began in 144 BCE. The project was supervised by the praetor Quintus Marcius Rex. The Aqua Marcia was 91 kilometers long. It was the longest aqueduct serving Rome at that time. The source of the Aqua Marcia was located in the Anio Valley, approximately 91 kilometers east of Rome. The intake was at an elevation of 318 meters above sea level. The water traveled primarily underground for the first 80 kilometers. The final 11 kilometers consisted of above-ground arcades. The flow rate of the Aqua Marcia was estimated at 187,600 cubic meters per day. This is equivalent to approximately 2,171 liters per second. The water quality was considered excellent. The Roman writer Frontinus, who served as water commissioner in 97 CE, described the water of the Aqua Marcia as the coldest and most wholesome in Rome. The Aqua Claudia was begun by the Emperor Caligula in 38 CE and completed by the Emperor Claudius in 52 CE. It was 69 kilometers long. The source was located near the modern town of Arceli, at an elevation of 320 meters. The Aqua Claudia included some of the most impressive arcade sections of any Roman aqueduct. Near Rome, the arcade reached heights of up to 27 meters. These tall arcades were necessary to maintain the gradient as the aqueduct approached the city. The channel had to remain at a consistent elevation while the ground level dropped. The arcade of the Aqua Claudia used a double-tier design in some sections. The lower tier consisted of larger arches supporting an intermediate platform. The upper tier consisted of smaller arches supporting the water channel. This design reduced the amount of material needed while maintaining structural integrity. The flow rate of the Aqua Claudia was approximately 184,280 cubic meters per day, or 2,133 liters per second. The water was distributed to various parts of Rome through a system of settling tanks and distribution basins. These tanks removed sediment and regulated flow. Settling tanks, called piscini, were built at points where the aqueduct changed elevation or direction. The sudden change in velocity caused sediment to settle out of the water. Workers periodically entered the tanks to remove accumulated sediment, typically once or twice per year. Distribution basins, called castella, were located at the terminus of each aqueduct. The castellum was typically a large tank built from concrete and lined with opus signinum. Water entered the castellum from the aqueduct and was then distributed through multiple pipes to different parts of the city. The castellum of the Aqua Claudia was located on the Celian Hill in Rome. It consisted of a rectangular tank approximately 15 meters long, 10 meters wide, and 3 meters deep. Multiple outlet pipes extended from the tank at different heights. This allowed water to be drawn off at different pressures. Pipes were made from lead, terracotta, or stone. Lead pipes, called fistulae, were manufactured by bending sheet lead around a wooden mandrel. The seam was soldered with a mixture of lead and tin. The mandrel was then removed, leaving a hollow pipe. Lead pipes were produced in standard sizes. The size was designated by the width of the lead sheet before bending. Common sizes included the quinaria, measuring 2.3 centimeters in diameter, and the centenaria, measuring 11.6 centimeters in diameter. Larger pipes were used for main distribution lines. Smaller pipes served individual buildings. Terracotta pipes were manufactured from clay. The clay was formed into cylindrical sections approximately 40 to 60 centimeters long. One end of each section was slightly narrower than the other. This allowed sections to fit together in a socket joint. The joints were sealed with lime mortar or clay. Stone pipes were carved from blocks of soft stone such as limestone or tufa. Each block was hollowed out to create a channel through its center. The blocks were laid end to end and sealed with mortar. Stone pipes were less common than lead or terracotta pipes due to the labor required to carve them. The pressure in the distribution system varied depending on elevation. Buildings at lower elevations received higher pressure. Buildings at higher elevations received lower pressure. To regulate pressure, bronze valves were installed at key points in the system. These valves, called cataracti, consisted of a bronze plug that could be raised or lowered to control flow. The plug was operated by a threaded bronze rod. Turning the rod raised or lowered the plug in the valve seat. When fully closed, the valve stopped all flow. When partially open, it restricted flow, reducing pressure downstream. Water from the aqueducts was distributed to 3 categories of users. The first category was public fountains. These fountains provided free water for general use. They were located throughout the city at intervals of approximately 100 meters. The second category was public baths. Rome had numerous public baths, ranging from small neighborhood facilities to massive imperial bath complexes. The baths of Caracalla, completed in 216 CE, could accommodate up to 1,600 bathers at once. The facility required vast quantities of water for its cold pools, warm pools, and hot pools. The third category was private connections. Wealthy individuals could obtain permission to connect a pipe from the public system to their homes. This required payment of a fee and ongoing water charges. The size of the pipe determined the amount of water that could be drawn. Frontinus recorded that Rome's aqueducts delivered approximately 1,127,220 cubic meters of water per day. This is equivalent to approximately 13,040 liters per second. The population of Rome at that time was approximately 1 million people. This provided approximately 1,100 liters per person per day. This figure is remarkably high compared to modern standards. Many modern cities provide 200 to 400 liters per person per day. The high figure for Rome reflects the water used by public baths, fountains, and ornamental displays, in addition to domestic consumption. Maintenance of the aqueducts was continuous. The office of the water commissioner, called the curator aquarum, employed approximately 700 workers. These workers were divided into two groups. The first group, consisting of approximately 240 workers, was employed directly by the state. The second group, consisting of approximately 460 workers, was employed by the emperor. The workers performed various tasks. Some inspected the channels for leaks and damage. Others cleaned sediment from settling tanks and channels. Still others repaired broken sections of channel or replaced damaged pipes. Access to the aqueduct channels was strictly controlled. Unauthorized entry was prohibited by law. Frontinus recorded that some individuals had illegally tapped into aqueducts to divert water for private use. Such theft was punishable by fine. The construction techniques used for Roman aqueducts spread throughout the empire. Aqueducts were built in Spain, France, North Africa, and the eastern provinces. Each region adapted the basic techniques to local conditions and available materials. The Pont du Gard in southern France is one of the best preserved Roman aqueducts. It was built in the 1st century CE to supply the city of Nemours, modern Nimes. The structure consists of 3 tiers of arches spanning the Gardon River valley. The lowest tier has 6 arches, each spanning approximately 20 meters. The middle tier has 11 arches. The upper tier, which carries the water channel, has 35 small arches. The total height of the structure is approximately 49 meters. The length is approximately 275 meters. The stones used in the Pont du Gard were quarried locally. They are a soft yellow limestone called pierre de Vers. The blocks weigh up to 6 tons each. They were fitted together without mortar. The precision of the fit holds the structure together through friction and gravity. The Segovia aqueduct in Spain is another well-preserved example. It was built in the late 1st or early 2nd century CE to supply the city of Segovia. The structure is approximately 17 kilometers long. The most visible section is a granite arcade that crosses the city center. This arcade is approximately 800 meters long and reaches a maximum height of 28 meters. It consists of approximately 170 arches arranged in 2 tiers. The granite blocks are fitted together without mortar, similar to the Pont du Gard. The gradient of the Segovia aqueduct is approximately 1%. This is steeper than most Roman aqueducts but was necessary due to the terrain. The steeper gradient also meant the channel could be smaller while maintaining the same flow rate. The abandonment of Roman aqueducts occurred gradually after the fall of the Western Roman Empire in 476 CE. Maintenance ceased in many areas. Channels became clogged with sediment. Arcades collapsed from lack of repair. Some aqueducts were deliberately destroyed during invasions. In Rome itself, the aqueducts continued to function, although at reduced capacity, through the early medieval period. The Aqua Virgo, completed in 19 BCE, remained in operation throughout the medieval period and still supplies water to Rome today. It feeds the famous Trevi Fountain. The study of Roman aqueducts by modern engineers has revealed the sophistication of Roman hydraulic engineering. Roman engineers understood principles of fluid dynamics, structural mechanics, and materials science. They applied this knowledge to create systems that functioned reliably for centuries. Modern aqueducts use different materials and construction methods. Concrete and steel have replaced stone and brick. Pumps allow water to be moved uphill, eliminating the need for gravity-fed systems. Pipes have replaced open channels for most long-distance water transport. However, the basic principles remain the same. Water must be transported from source to destination. The system must be watertight. The gradient must be carefully calculated. Maintenance must be regular and thorough. The construction of a major aqueduct required substantial resources. The Aqua Claudia took 14 years to build, from 38 to 52 CE. Thousands of workers were employed. Stone had to be quarried and transported. Concrete had to be mixed and placed. Channels had to be excavated through hills and across valleys. The cost of aqueduct construction was significant. Ancient sources rarely record specific costs, making precise estimates difficult. However, comparisons with other large projects suggest that a major aqueduct might cost several million sesterces. For context, a skilled worker might earn 3 to 5 sesterces per day. The economic impact of aqueducts extended beyond construction costs. Reliable water supply enabled urban growth. Public baths provided recreation and hygiene. Industrial processes such as fulling cloth and tanning leather required large quantities of water. Mills powered by water from aqueducts ground grain into flour. The social impact was equally significant. Access to clean water improved public health, reducing waterborne diseases. Free public fountains provided water to all residents regardless of wealth. This represented a form of public welfare. The aqueducts demonstrated the power and generosity of the state and emperor. The decline of aqueduct systems in the post-Roman period led to a decline in urban populations. Medieval cities were generally much smaller than their Roman predecessors. The revival of large-scale water supply systems did not occur in most of Europe until the 18th and 19th centuries. The ruins of Roman aqueducts have served various purposes over the centuries. Some have been incorporated into later buildings. The arcade of the Aqua Claudia was incorporated into medieval fortifications. Sections of aqueducts have been used as roads or bridges. In some cases, aqueduct ruins have inspired modern engineering projects. The study of Roman concrete has influenced the development of modern hydraulic cements. The design of Roman arches has informed modern bridge construction, particularly in the 19th century. Archaeological investigation of Roman aqueducts continues to reveal new information. Excavations uncover sections of channel previously unknown. Analysis of deposits inside channels provides information about water sources and treatment. Study of construction techniques enhances understanding of Roman engineering methods. The legacy of Roman aqueducts extends beyond engineering. They represent the organizational capacity of the Roman state. The ability to plan, fund, and execute projects spanning decades and covering hundreds of kilometers required sophisticated administration. The aqueducts also represent a commitment to urban infrastructure. Roman authorities invested substantial resources in systems that provided no direct financial return. The benefit was social stability and enhanced quality of life for urban residents. This completes our examination of Roman aqueduct engineering. The principles of gradient, the properties of opus cementitium, the design of settling tanks, and the distribution of water through castelli. From the Aqua Appia in 312 BCE to the structures that remain standing today, Roman aqueducts demonstrate technical achievement applied consistently across centuries.